Hello everyone! This is a hands-on tutorial on gradient descent, where we will implement it in Python from scratch. Now, of course, you can simply use a ready implementation of gradient descent by one of the many machine learning libraries. But I find that writing the code yourself is the best way to understand how an algorithm really works. So in the first part of this video, we will define gradient descent and write the code for it. Then in the second part, we will apply our code to a real-world problem of classifying handwritten digits. Specifically, we will use gradient descent together with logistic regression to tell if each image is 0 or 1. So what is gradient descent? Generally speaking, it's a minimization algorithm that is iterative and always follows the steepest descent. Now let's unpack what this actually means. Say you have a function that you want to minimize. We start at some random location, and then on each iteration, we take a step trying to improve on the previous iteration. This is why we say that gradient descent is iterative. And steepest descent means that each time we take a step, we move in the direction that brings us down the fastest. This direction is the opposite of the function gradient, which is where the name gradient descent comes from. We can summarize it with the following pseudocode. We first initialize x randomly, and then we repeatedly take steps in the steepest descent direction. If you want a more detailed explanation of gradient descent, I made a full video on it, which you can watch by clicking on this link. Now we're ready to jump into the code. So here we are in a Google Colab notebook, and by the way, I'm going to be making all the code available on my GitHub, and you can find a link in the description below. So the first thing we're going to do is we're going to execute all of these import statements to make sure that the libraries that we need are available for us. And first, we will implement gradient descent for functions of just one variable. In practice, it's more common to work with multidimensional or multivariate gradient descent, but it's much easier to first build a simple case for just one variable and then build on top of it to extend to multiple dimensions. So imagine that this is the function that we need to minimize. It's the quadratic function. It has a very well-known U shape, which we can easily demonstrate. We just need to execute this code, and that's the graph of our function. So the algorithm is iterative, which means that we're going to initialize x somewhere here or here, doesn't matter. We initialize it randomly, and then it should descend gradually and eventually find the lowest point of the function. So this is how we can verify the correctness of the algorithm. So the first thing we're going to have to do is we need to implement this function. So we would say def f of x, and we return x squared. We execute that. So now this function is available for us. So now, since the gradient descent requires the gradient, or just the derivative in case of one-dimensional function, we also need to implement the derivative function, which we call df dx of x. And according to calculus, this is the formula for the derivative. So we just return that. So now we are ready to implement the gradient descent. So we create a new cell, and the first thing we're going to have to do is we initialize the initial value of x. So we can give any value, let's say 5. Now we need to define a couple of parameters for the algorithm. The first one is going to be the learning rate. So it's going to be called the learning rate. So what it does, it controls the speed of execution of the algorithm. So every time we make a step, we are going to multiply by the length of the step by the learning rate. So this means that the higher the learning rate, the faster the algorithm will execute. But at the same time, if the step size is too large, then the algorithm might not converge, for example. On the other hand, if the step size is too low, then the algorithm is going to take a very long time to converge. So in general, you try to find a sweet spot here. So I think for our task, 0.1 will be reasonable. Now the next parameter is just the number of iterations of the algorithm, which we can set to 25. So now let's run the algorithm. So first we initialize the value of x to x0, which is 5. And then we run the for loop. Oh, that's the wrong name. Okay, so actually let's call it n steps. I think it's a better name. Okay, so the first thing we're gonna do is we will print the current state of the algorithm. And why we want to do this is because, by the way, here's a typo. That way it's better. So this is a very helpful information because it can show us whether the algorithm has converged or, for example, if there is any problem with the execution. So what we do here is first we print the iteration number, then we print the current value of the argument x, and then finally we print the value of the function. And the goal is that the function value is going to converge to 0. So now the next step is to find the gradient. So we need this because we use gradient to find the direction where to step. So gradient would be given by our function df dx. So we put it here. And then the most important part of the algorithm is to update the argument. So x minus gradient. So this means that on each iteration we're going to move in the direction of the negative gradient, because in the direction of the gradient the function is increasing, and in the direction of the negative gradient it is decreasing. And of course we shouldn't forget to multiply by the learning rate. So looks good to me, and let's try to run it. All right. So that looks exactly like what we would want to see. So as you can see, the value of the function starts relatively high, and then it keeps going down, 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 and down until it gets very, very close to 0. And actually, we only ran it for 25 iterations, and if we were to run it further, it would keep dropping. And if you look at the values of the argument, we start at 5 because that's the value with which we initialized, and then we keep approaching 0, which we know is the optimal value, because if you look at the shape of the function, that's where 0 is, and that's where the lowest point is. So basically what happened is that we started at 5, which is somewhere around here, and then we kept on moving in this direction until we almost reached 0, at which point we just stopped running the algorithm. All right, so now we have a working version of the algorithm, but the problem is that it only works for the quadratic function. So it's not going to work for anything else. And actually, if we want to try it for many different functions, it would be really cumbersome to always write all of this code. So what we're going to do instead is we will take, I would call it a library approach, and we're going to implement a generic function that will take a function object as a parameter, and as another parameter it would take the derivative of that function. And then for any function that is smooth enough and is of good enough shape, it will be able to find the minimum using gradient descent. So the way we're going to do it is that we are going to copy this code and we'll create a new cell, and then we will convert this code into a function. So we need to name it something. So I would say grad descent seems like a reasonable name. And of course this stuff has to be indented. And the first parameter to this function, the first argument, is going to be the function object of the function that we want to minimize. The second one is going to be the derivative or the gradient. And now we can also pass these parameters that were hard-coded previously as parameters that can be adjusted to this function. So we take x0, then we take the learning rate and the number of steps, and we pass all of them to the function so that it can be changed in whichever way suits the function that we're trying to minimize. So now an important thing is that here, when we calculate the gradient, instead of this function, we should actually pass the derivative. And then here, instead of f of x, it should be func. So there is one more thing that I want to do, which is not necessarily related to gradient descent, but I want to make the output look more or less presentable going into the future. So I will add this function in here. You don't really need to bother reading this. This is just to make our output not look ugly for different forms of input. And then instead of this printout, we will insert this code here. So it does pretty much the same way as the printout statement before, but in a slightly more flexible way. Okay, so we execute that. And now I want to make sure that this generalized approach works in the way that we want it to. So we have to test it. And I will test it with the same code. So I will again take this function and its derivative. I will pass them to this generic function of gradient descent, and they should converge to the same value. Except I forgot the return statement. So let's grab this function here. And then what we need to do is, instead of func, we will pass in our function f. Instead of derivative, we will pass df dx. For x0, I would say this time, let's pass something slightly different. Let it be -7. The learning rate, I would say the same. And for the number of steps, well, -7 is slightly further from the optimal point than 5. So instead of 25, let's take 35 steps. And now, since this is a function, we need to assign the output value to some variable. Let's run this. And let's see. So again, like in previous case, we start pretty high, then we start going down, down, and we get pretty much to 0, very close. And if we look at the at x, then we start at -x because that's the value that we passed for, like, to initialize the algorithm, and then we gradually converge to 0. Again, this is not precisely 0, but given the trend, if we were to continue to run it, we'll get closer and closer to 0. So now that we have this generic implementation of gradient descent, we are ready to switch to variants of gradient descent that you are more likely to see in practice. Instead of one variable, now we're going to look into the multivariate variant of gradient descent. And basically the only difference is that now f of x is allowed to depend on multiple variables, and it can be quite a lot of variables in practice. So the first function we're going to look at is this, which is the square of the Euclidean distance between the vector x and the vector of all ones. And you can write it in an open way like this. So basically, it's like the way you calculate this is you take every coordinate of vector x separately, you subtract 1 from that coordinate, you square it, and then you take the sum. So it's a very well-known function. It's convex, so our algorithm should be able to find the optimal point. So the first thing we're going to do is we have to implement this function. So say d f, and well, what would be a reasonable name for this function? Let's say fmult, to indicate that it's a multivariate function of x. So remember, this time x is actually a vector, and now we need to return this value. So there is a very useful library called NumPy. So we actually, at the top of the file, we imported it like this: import NumPy as np. And if you read machine learning code, you will see this kind of import statement a lot, because it's a very useful library for dealing with vectors. So, and this library has the following function. It's called the norm, and it's very useful when you have to deal with any sorts of Euclidean distances. So basically, this expression here inside is a norm of the difference between these two vectors, and then we just need to square it. So we execute this. So now this function is available to us, and now we need to implement the derivative, or since we are in the multidimensional case, it's the derivative is called the gradient. So, and the gradient is going to have as many dimensions as there are elements in vector x. So from calculus, we know that this is the formula for the gradient of this function. So the way you read this is that this is an n-dimensional vector, and this is the formula for each element of this vector. So we create another cell, and then we need to implement the function for, let's call it gradient, for the gradient of this function. And I think this is the way it should look. Execute that. And now let's copy this thing for testing. So we create another cell, copy this. And now the important part is that we need to replace f and df dx with our new functions. And let's see what happens. So now I think the learning rate and the number of steps could remain the same, but it is very important to change the initial value for x, because we are no longer in the one-dimensional case. So instead of a number, we actually have to pass in a vector. So again, it's very convenient to use the NumPy library, and we just pass in some random vector, I don't know, 2.4, 1, or -1. So it's a 5-dimensional vector of some random values, but we should still be able to converge to the optimal point. So we run this, and let's see what happens. Again, like with previous cases, we start pretty high because this was not an optimal point. It was just somewhere, some random point. And then we drop pretty quickly. And at the end, we are again very close to 0. And now here with x, it looks a bit more interesting because now we have 5 values for x, because now x is a 5-dimensional vector. So we start with this vector, which is pretty much the vector that we passed in. And then as we keep iterating, we can see that we are pretty much getting ones in all elements of this vector. So we're converging to the vector of all ones. So to see why this is the case, if you look carefully at this function, so imagine an n-dimensional space, and this is a distance, or well, it's a square of a distance between some vector in this n-dimensional space denoted by x and a vector of all ones. So a distance can never be negative, so we already know that this expression is greater or equal to 0. And then let's see what happens if we plug in a vector of all ones instead of 1. So since this is also a vector of all ones, all elements would turn to 0. And then when we calculate this sum, it would also be 0. So now if we know that this vector can never be negative, and it assumes a value of 0 for x being a vector of all ones, this means that this vector actually minimizes the function. So this is the right answer. We get the vector of all ones. All right, so now we are ready for a real-world application. So what we're going to do is we will classify handwritten digits. And for that, we will use one of the most famous dataset that you will see a lot in machine learning or computer vision literature. And it's called MNIST. So it's a collection of handwritten digits from American Census Bureau employees and American high school students, where each image was scaled so that it has the size of 28 by 28 pixels, and it's in black and white. So this is what these images look like. And we will implement the logistic regression classifier, and then we will use gradient descent to actually train this classifier. Because the reason I chose this one is because it has a convex cost function, and it really showcases what gradient descent can do. Now, it's a binary classifier, which means that we have to restrict ourselves to only 2 classes. So for this reason, we will only select images that represent zeros and ones, and then we will train the classifier to distinguish between them. So the first thing we need to do is get the data. So unfortunately, there have been some problems getting the data from the official website, and there are other ways to get it, so we will just download it from PyTorch. Okay, so I think it should be done by now. All right, so now that we have downloaded our data, we should have 2 datasets available. One is called train set, and the other one is test set. And we will train our model on the train set, and then we will test it. We will test its performance on the test set. But before we can do that, we have to convert both of them to the NumPy format. So the way to do this is to call the NumPy function. So train set data and NumPy, and okay, so it's working, and you can see that we actually get an array back. So let's assign this to a variable. Let's call it, let's say, train images. So these are the images themselves, and then we also need labels that would tell us if each image is a 0 or a 1. So that would be train y, and to extract it, we would, instead of data here, we would take targets. And then the same thing, just convert it to NumPy. We run it, and it's working. So we do this for the training data, and now we should do exactly the same thing for our test data. We'll just replace here with test, and it would be test here as well. Test here, and test here. So now we have all of that available. So now let's explore the data a little bit. Let's see, for example, what shape it has. So let's take our train images, and in NumPy you can just type shape, and it's going to show you the dimensionality of the data. So this means that array train images has size 60,000 times 28 times 28. So in other words, 60,000 images, and each image has size 28 by 28 pixels. Now we can do the same thing for labels, and we get that the array of labels has 60,000 elements. So that means 1 label per image. So now I find that in NumPy, it can be a bit cumbersome to work with one-dimensional arrays represented in such format. Just basically because of the way operations are structured in NumPy. So it's convenient in practice to convert one-dimensional arrays to one-dimensional like column matrices or column vectors. So just to show you really quickly, if we have an array of size n, like here, for example, n is equal to 60,000, then I find it better to actually convert it to shape n times 1. And then just treat it as a matrix with n rows and 1 column. So, for example, if we had an array of 5 elements, we would rearrange it like this. So let's then convert our labels to column matrices. So all we have to do is just add one additional dimension to train y and test y. So at first we're going to test it on train. So the way you do this in NumPy is with the following syntax. So you just add a new axis, and this column here just basically means take all the elements in the array. Okay, so let's run this, and now let's see what happens to the shape. So as you can see, now it has the shape n times 1, so it's become a column matrix. And we can do exactly the same thing with test labels. All right, so now what we have to do is, remember, we need only 0 and 1 images, but for now we still have all the 10 digits represented in our dataset. So what we have to do is filter on labels of 0 and 1. And since we have to do it for both train and test datasets, I'm going to create a function that we can call for both of them. I'm going to call it get binary images. And the first argument would be the data itself, and then the labels that we will use to filter the data. So the first thing we have to do inside the function is, funnily enough, actually convert the labels back into the vector format. So we should get rid of this extra dimension because we will be using it for indexing. Okay, so for that, we're going to use the function numpy squeeze labels. So what this function does is simply it gets rid of all the singleton dimensions. So it will just erase this thing here. And then we can create our index by filtering on lab either being equal to 0 or being equal to 1. So now IDX has indices of elements in the array, that is indices of images that are either 0 or 1. And now the only thing we need to do is just return data and label filtered on this index. Okay. So now we can actually do the filtering. And for that, we need to call this function. So we have to pass in train images and train y. Oh no. and let's just assign it to them. So now let's actually verify that we are doing everything correctly, that we actually got zeros and ones. And to do that, we will plot images and see if they are actually of 0 and 1. So we will plot 10 images, and we will do this in a loop. So matplotlib, which is here abbreviated as PLT, is a very nice way to quickly plot something in your notebook. So here I'm creating an n divided by 2 by 2 dimensional grid, and I'm indicating that this subplot is going to be at position i+1 inside that grid. And now what's left is to show the image. So that would be train images. With index I, and we don't need to show the axis. All right. Okay, so that looks like our filter works, and we just need to also filter our test data. So that would be test images and test Y. And we're just going to run it. All right. So now, before we start working on the logistic regression model, there are two more things that we need to do to our data to prepare it properly. First, we need to reshape both the train and the test data sets from 3-dimensional arrays into 2-dimensional arrays. And once we've done that, we'll need to standardize the data to make it easier for the gradient descent algorithm to converge. So first, let's create a new cell and check what the shape of the data is like. So train images dot shape. Okay, so as you can see, we have a little over 12,000 images, and every image is of size 28 by 28. But we need to convert it into a 2-dimensional array or into a matrix, which means that we need to collapse these 2 dimensions into one. So basically, one image would represent one row in the data. So, and again, we can do it using the reshape function of NumPy. So we just need to provide the shape. So the first dimension is going to stay exactly the same because this is just the number of images in the data, in our data. And for the second image, for the second dimension, we're going to give -1, which basically means take all the elements of these 2 dimensions and collapse them into a single dimension. So it's just going to become one row. So we execute that, and now let's verify that the shape of the resulting array is what we expected. And as you can see, the first dimension stayed the same, and these 2 got collapsed into one. So now we need to copy this and do the exactly same thing to our test data. So that would be test images, and then we need to also place it here. Okay, so we have successfully reshaped our data, and now we need to standardize it. Now, generally speaking, there are many different ways you can standardize or normalize your data, but I found that in our example, it's enough to just subtract the mean of the data and then divide it by the standard deviation. The only thing I would say is important is to keep these values that you use for standardization the same between the training and the test datasets. So first, let's calculate the mean. So that would be train images and NumPy mean. And then we also need the standard deviation. And then we can transform the data by subtracting the mean and then dividing by the standard deviation. And let's call it train X. Okay, so now we can do exactly the same thing with the test dataset. And we are using here the same values for mean and standard deviation as we did for the train dataset. So here we would have test images. All right, so now we have our data prepared and we can start working with the model. So for our image classification problem, we're going to use the logistic regression model. And it's a binary classifier, which means that when we give it our image as the input, it's going to output a label, which is going to be either 0 or 1. And it's really important how it actually does it, because it's such a ubiquitous model in machine learning. So it takes the vector x, the input, and then it applies a linear function to it. And this linear function has two parameters, the vector of weights and the bias, which is just a number. And when we train logistic regression, then it finds the best values for these parameters so that it can later use them to make predictions. So the linear function is calculated by first computing the inner product of the input vector x and the vector of weights, and then adding the bias. So just in case you need a refresher on what the inner product is, we just need to calculate products of elements in x and w and sum them up. So you take the first element in x, you multiply it with the first element in w, then you do the same thing for the second element, and so on, and you sum them all up together. And then finally you add the bias. And the idea of logistic regression is that we want to use this output of the linear function to predict the label of that image. But we do have a little problem, which is that the linear function can output any number, any real number, not just 0 and 1. So how do we get it to output a label? So the answer is that first we need to apply the logistic or so-called sigmoid function to the output of the linear function. And the great thing about the sigmoid function is that its output is always between 0 and 1. And that means that we can actually interpret it as a probability. So the probability that the model thinks that the label is 1. And if this probability is greater than 50%, then we should output 1 as the label. And if it's smaller than 50%, then we should output 0. Now, of course, our probabilities are between 0 and 1, so our threshold would be at 0.5. So this means that if h of z is at or above 0.5, then we output 1. And if it's below that, then we output 0. So you can kind of think of the whole thing as a pipeline. You get the vector in, you apply a linear function, then you apply the sigmoid, and then you threshold it at 0.5. And then you get your label as the output. So this is how you process a single image. But for the gradient descent to work effectively and take full advantage of hardware and of great linear algebra libraries that we have, we should process the images, like many images together. And the way to do this is called vectorization. So we aggregate the input images in a matrix. So here we have m images. So each row corresponds to an image. And then there are going to be as many columns as there are pixels in that image. So basically each row is an image. And then we need to multiply this matrix of input images with the vector, with the weight vector of the model. And then we add the bias, and then we obtain the outputs of linear function for each of the images. And then we can do the remaining steps of applying this sigmoid to each one of these z values, and then threshold each one of them. So again, multiplying a row in a matrix and a column vector is basically the same as calculating the inner product here. Okay. So now there's one little, I would say, trick that we need to know. It's kind of inconvenient to work with bias, because it would be very nice to just write everything in terms of these inner products, because then it's very easy to vectorize, it's very easy to work with it. But this kind of throws us off a little bit. So there is actually a way to get rid of the bias. So the way you do it is that you take your input vector, so all the pixels of your image, and you add a constant to all of them. You just add one dimension and you set it to 1. And then you can rewrite all the parameters of the model as a single vector of weights. So we will have the first n values occupied by the regular vector of weights, but the final value is going to be the bias. And the trick is that now we can rewrite our formula for the linear function as just the inner product without the bias. Except that now we are working with n+1 dimensional input vectors and n+1 dimensional weights. And I also made a video on logistic regression with visual explanations. So if you would like to watch that, you can click this link. Okay, so now it's time to get to the actual implementation. And the first thing we're going to do is we will transform our data to accommodate the bias trick. So first, let's save the number of images in the train dataset, and then we will transform the data. So it's it's convenient to use the horizontal stack function from NumPy, because basically what we need to do is just append a vector of all ones to the train X matrix. So that would be train X, and then NP1s of size n train times 1. And then we should do exactly the same transformation with the test dataset. Here is going to be test X. Here's test X. And here, and test. Okay. So now that we have our data transformed, we can implement the actual prediction function. So for now, we assume that we have learned the weights, all the parameters of the model. So now we only have the weights W. We don't have to deal with bias anymore. But for convenience, I'll just work with X and W. We can drop the apostrophes. Okay. So let's first implement the function that is going to output the probabilities. So by that, I mean this H function. So it's a composite function. So first it calculates the linear function, and then it applies the sigmoid function on top of it, and we will implement both of them. So let's call it H, and it should accept the vector of weights, the parameter of the model, and the data. Now, let's first do some sanity check just to make sure that that all the dimensions are right, because when working with multidimensional data, it's very easy to make mistakes with that. And we're just going to assert that the shape of W is, I think it's going to be n features times 1. This is because we are calculating the inner product, and for that both vectors have to have the same dimensions. And what we're going to return is the logistic function of 1 plus the exponent of negative z. And we need to define z. It's going to be the dot product of x and w. All right, so this looks about correct, but it doesn't mean that it actually is correct. So let's test it a little bit. At least we need to make sure that the output values of this function are between 0 and 1, because that's what sigmoid outputs, and that's the only way we could interpret them as probabilities. So let's generate a random vector for w, because this condition should be satisfied regardless of what w is. and we just need to make sure that the dimensions are right. So the number of dimensions should be the same as the number of pixels, which is the number of elements in one row of train X. And the second dimension should be 1. All right, so let's calculate the output of this function. So W, and then we apply it to the entire train dataset. Okay, and now we need to make sure that the minimum and maximum values are both between 0 and 1. So the minimum value is calculated with numpy min, and we can also calculate the maximum value. And now let's run it. All right, so the minimum is very close to 0, but it's still kind of positive, and the maximum is 1, which is actually a numeric error. It's not exactly 1, it's something like 0.9999999, but it's good enough for us. It doesn't go above 1. Okay, so now we will use this function, and whenever we need to make predictions, once we have learned the right value for W, we'll just apply this function to X and then threshold the output at 0.5. But we still haven't learned the vector of weights, W. And the way we can do it is we need to minimize the so-called cost function or objective function. You can kind of think of it as the measure of the error of the algorithm, of how much it is wrong. And this is what it looks like for the logistic regression model. Now, I'm not going to go deeply in detail on why it looks like this. But one piece of intuition is that minimizing this function is actually equivalent to finding the vector W that would maximize the chance of observing the training data. So just a quick notation guide. When we have superscript I, that means that it relates to the ith training example. So yi is the ith label, and hi is the result we get when we apply function h to the ith image. Okay, so now we need to implement this function. I'm going to call it j. So we pass in the vector of weights, the data, and the labels. And as usual, the first thing we're going to do is we will make sure that our dimensions are consistent. So in this case, we're making sure that the number of labels is the same as the number of training examples, because if not, then we have a problem. Now we are going to calculate h using the function that we have earlier defined. So now there is one important thing that you need to keep in mind when implementing logistic regression, which is that when the output of h is very close to 0 or 1, then these logs, they might not work the way you expect because of numerical issues. So what we can do is we can clip the values below and above so that they never get too close to 0 and 1. So I will introduce a very small parameter and I will use it to remove everything that is very close to 0 or 1. So there was a function called clip in NumPy, and we can use EPS below and 1 minus EPS above. So basically everything below EPS would be set to the value of EPS, and anything below this value would be just thresholded at 1 minus EPS. Okay, so now that we've done that, let's calculate each term in this expression. So that would be y times, I'm just basically following this this formula now. So that would be np log of h plus 1 minus y times np log of this. And now what we need to return is an aggregation of these terms. And now, unless I made a mistake somewhere, this function should do exactly what this formula prescribes. Okay, and now we just need to test it. So I have a little test which just feeds in some random, pretty much random values, and the goal is just to make sure that when dimensions are right, that the code runs and doesn't crash. Okay, so it looks reasonable. So let's say that we have the cost function implemented. And now the most important thing for the gradient descent is that we need the gradient to be able to make updates. And this is what the gradient for this cost function looks like. All right, so let's quickly try to understand why this expression for the gradient even makes sense. So imagine that for some image, the model gave the right label, and it was also very confident about this prediction. So in this case, h would be very close to y. So this part would be very close to 0, and its contribution towards the gradient is going to be very, very small. But on the other hand, what would happen if the model were to give a wrong prediction, but would also be very confident about this wrong prediction? So in this case, this would be either 1 or -1, or very, very close to it, and would actually make a big contribution towards the gradient. And that contribution would also be proportional to the value of the respective feature. Okay, so now hopefully we have at least some intuition for the gradients, so we can implement it. Okay, so we call it grad, and we pass in our usual data. And as usual, first we are going to make sure that nothing is wrong with dimensions. Very important. So the number of labels should be the same as the number of images in the data. Then we're going to calculate h using our h function. And then we return this expression. So it's going to be 1 over m times, and then the inner product is calculated with np dot h minus y. So it's just convenient to calculate like this. And now we need to test it. So let's initialize w to some random vector. Yeah, I'm not really verifying the correctness of these of the gradient. I just want to make sure that it runs without problems and that this assert doesn't get triggered. And yeah, now we can just call grad. Oh, there was a typo. Train X and train Y. Okay. Oh no. And it didn't work. Right, because I forgot to pass in W. That's why you do tests. Okay. Well, I guess that's reasonable. But now let's try to actually run the gradient descent. Now, conceptually, it would make sense to just use the function for the gradient descent that we defined earlier, and it would work. But there is one specific problem with it, which means that we need to make a small amendment. So specifically, on each iteration, we print a lot of information about the current state, and also we print the current value of the argument. But now this argument is going to be the entire image. It would have like over 700 pixels. So we would, if we were to do that, we would just drown in the output. So we need to make a small adjustment. So I'll take that and let's get here and let's redefine it. So this can stay the same. So basically what I'm gonna do is I will introduce a flag that would tell us whether we want to print the argument. So by default, it's going to be true. So the previous code should still work. And now what I will do is I will change this line. So so like this, if the flag is true, and otherwise it's just empty. And it should work like this. All right, so we redefined that. And now it's time to learn the vector of weights. Let's find vector W. Okay, so first let's define the number of features. So that's going to be train X, basically the number of columns. This is just for convenience. And now we are gonna copy this thing. Okay, so in place of func, we are going we need to pass our function j, but we cannot pass it directly because it also depends on two further parameters. So we say func, we can use a lambda function, and then we'll pass the function j with train x and train y. Okay, then derivative would be, we can do it similarly, so we'll use the lambda. And here, of course, instead of j, we need grad. Then, I guess here it should be equal. x0, let's pass in, let's start with a vector of all zeros. I think it's reasonable. Okay, here we can use n features times 1. Learning rate, let's use 0.1 again. And now I think we need more steps because it's a high dimensional space. The convergence will probably be a bit slower. And we want to set the flag to false because we don't want to have too much output. Okay, let's try it. All right. So it's doing something. Okay, but in general, it doesn't look too bad. Like again, we start high and then we drop immediately and continue dropping, although we are quite close to 0, so these gains are probably not that significant. Okay, so at least the gradient descent seems to be working. So now let's see how well we actually performed. So we are going to evaluate the errors. So for that, we first need to import the metric. And this metric basically tells us how often we are right. So first we need to make the prediction. So we call h with w optimal that we've just learned with code on train, because so this is to calculate the train error. We'll start there, and then we will calculate the test error as well. So as you remember, we predict 1 when we are above the threshold of 0.5, and now we need to convert this to type int. Okay, and now let's print it. So train precision. And that would be the precision score of the true labels, train y, and our predictions. And okay, let's actually run it. Okay, so this is how often we are right, which is, I would say, almost all the time, which sounds good. But let's see how well we do on the test set, which is actually a more important measure. Okay, so Now we need to adapt this piece of code to work with the test data. It's going to be test here, and we also need to make sure that we're using test labels. Test X. But actually, while filming this, I realized that it's actually not going to work because I forgot to filter the test data on zeros and ones. So actually, it's also test Y here. So test Y has all sorts of labels, not just zeros and ones. So we need to go back to filtering, and I first need to run this piece of code, and then need to also do the binary trick for the test data. So now we go back, and now hopefully it's gonna work. Okay, so it works, and test precision is, as expected, lower than the train precision, but the difference is really minor. All right, so I would say now is the time to actually see the fruits of our labor and print the images. So first we will show images for which our model says that they are 0, and then separately we will show images for which we predict 1. So we do need to write some code, but I thought that I would spare you the typing and just insert the ready code because, well, there is actually nothing special about it. And yeah, that's what it looks like. So as expected, for images for which we predict 0, they actually do turn out to be 0. And the only thing that's left is to do the same thing for ones. And there it is. So it looks like our model is working correctly. So the gradient descent algorithm seems to have worked. Now I hope that you enjoyed this little walkthrough through the algorithm and the notebook. But I would really like to emphasize that gradient descent is a very versatile algorithm, and we barely scratched the surface here. There are a lot of variants of it, a lot of things to learn, and I really encourage you to go and look in the literature how it's used, read the code. It really pays off. And other than that, I hope that you enjoyed this tutorial, and I will probably post more tutorials like this. And if you can think of a topic that you would want covered next, then let me know down in the comments below.